Multi-messenger prospects for probing the interstellar environments of luminous infrared galaxies by Alice Owen from NPHU.
Thank you. And these are the PowerPoint. Oh, it's huh?
You mean PowerPoint?
Yeah. Okay. Thank you very much. So for those of you who so for those of you who don't know me, I'm Alice Owen. I'm a Senior Fellow at National Tsinghua University. For those of you who do know me, you may be wondering what I'm doing giving a talk at this conference, given I work on high-energy theoretical astrophysics, particularly cosmic ray propagation and interactions. And the reason is Songjin kindly invited me to give a talk and asked me could I talk about something to do with galaxies and cosmic rays, and I said yes. And I thought it'd be a really nice opportunity to talk about the potential that the wealth of carry legacy data and the catalogs that have been derived from this can actually help us to start to tackle some really pressing problems on the high energy side. And one that particularly came to mind in the last couple of weeks since Songjin asked me to give this talk was the issue of the tension between the diffuse neutrino background and the diffuse gamma ray background. So these are thought to have a hadronic origin. They're thought to should I start again? So these are thought to have a hadronic origin, at least in part. And there's an issue in that, trying to mold these in a way that's consistent with the data introduces some amount of tension. So, the pressing question at the moment is how to find a model that's consistent with the diffuse neutrino detections that doesn't massively overpredict the gamma ray flux in this detected with Fermi. And in recent months, maybe even weeks, people have started introducing a few different, say, exotic models. One is spectral blending, and this is the idea of saying, maybe the cosmic ray flux in star-forming galaxies has a number of different spectral indices, and you blend all of these together rather than just assuming a single spectral index. And if you adopt certain combinations of different spectra, then you can more or less reproduce the proportion of neutrinos being produced to gamma rays without over-predicting the gamma rays. Other groups have suggested maybe there's exotic acceleration mechanisms that can push up the highest energy of the cosmic rays of these host galaxies, so that more neutrinos are produced and you don't end up overproducing the gamma rays. But I kind of think that maybe these guys are jumping the gun a little bit. Sure, it's important to look at the theoretical side, but I think there's one thing that hasn't been explored in as much detail, and I think it should be explored in more detail, which is the role of luminous infrared galaxies. I think these could be quite a natural explanation to this discrepancy. And this is because, firstly, luminous galaxies, infrared galaxies, have a high star formation rate. This high star formation rate translates into an abundance of stellar end products. These stellar end products, particularly things like supernova remnants, are very effective cosmic ray accelerators. So these environments are likely to have abundant cosmic rays. If there's lots of cosmic rays, there's going to be lots of cosmic ray interactions. In these environments, hadronic interactions are going to dominate. And the interaction rate is set by the cosmic ray density and hence the star formation rate. So you have quite a direct scaling between the cosmic ray interaction rate, the hadronic interaction rate, and the underlying star formation rate of these environments. So the way in which the interactions work is you have a high energy proton provided by the cosmic rays interacting with an interstellar proton. This is maybe a nucleus in interstellar gas. And this goes on to produce these excited delta resonance particles, which then go on to decay to produce charged and neutral pions. So the neutral pions produce gamma rays. This is where the gamma ray emission the diffuse gamma ray emission in the Milky Way comes from. It's been detected from nearby star-forming galaxies as well, and it's thought to produce a substantial fraction of the unresolved extragalactic gamma ray background, particularly at sort of tens to thousands of GeV energies. Alternatively, the decay of these charged charged planets can lead to the formation of further gamma rays, leptons, which can thermalize quite quickly in the interstellar medium, and of course neutrinos. So suddenly we have these interactions which are a source of both gamma rays and neutrinos as well. So the gamma rays themselves actually they don't freely escape from their source environment. So if you have a gamma ray photon, it will interact with ambient radiation fields to pair produce. Those ambient radiation fields can be provided by CMB permeating the galaxy. It could come from starlight. It could come from extragalactic background light outside of a galaxy, or most importantly, it could come from reprocessed stars by dust. And this leads to pair production. The produced electron-positron pairs actually can thermalize relatively quickly over a distance of about 0.1 kiloparsecs within the host galaxy. So this process within the dense conditions of an interstellar medium effectively attenuate that gamma ray emission. For those gamma rays that can escape, the same process operates in the low density conditions of the IGM as they propagate cosmologically to reach us, which effectively reprocesses the gamma ray spectrum a little bit. And I'll talk about that a little bit more later. But for now, let's look at this internal attenuation. How severe can it be? So if we have the gamma rays being produced over a range of energies up to like 10 to the 6 GeV or so, we can look at the effective attenuation rate by characterizing a path length of the gamma rays within the host environment, and consider the processes, the interactions with various radiation fields that can lead to the attenuation of those gamma rays. So here we have the attenuation of gamma rays with ambient starlight. So that's moderate, and it can cause some amount of attenuation in the spectrum of these intermediate energies. Interactions with the CMB come into play at higher energies and are actually not that important. Most important of all are the interactions with dust reprocessed starlight, and this almost completely attenuates the gamma ray emission from a galaxy above 10 to the 4 GeV. And that's actually quite telling, because that is the energy at which things become problematic for gamma ray emission in terms of the flux that we're getting from the gamma ray background. So it's maybe not a coincidence that this energy cutoff is the same as the energy cutoff that we're seeing in the gamma ray background. So how does the spectrum look like? Well, in grey here I have the gamma ray, let's say, production spectrum. If there was no attenuation, the emission of gamma rays from a luminous infrared galaxy would look like this. However, if you start to account for this attenuation, then you get a bit of a dip due to the stellar radiation fields, and a big dip due to this dust reprocessing. So the normalization of this spectrum is set by the cosmic ray energy density, which in turn is set by the star formation rate of the host system. And the spectral index is set by the underlying spectral index of the cosmic rays. So this is relatively well constrained theoretically, and also by observations within the Milky Way. So yeah, the interaction with starlight is set by the parameters to describe the thermal radiation field due to stars, and similarly with the dust reprocessed starlight. So we can see here that actually understanding the characteristics of the dust emission, the infrared emission from a star-forming galaxy or a luminous infrared galaxy, can tell us quite a lot about the amount of gamma rays that can escape. As for neutrinos, well, the situation's a little different. So this is the neutrino spectrum compared to the gamma ray spectrum. So here, I don't know what colour that is, maybe brown, we have the neutrino production. And unlike gamma rays, these are not attenuated at all. They're just able to completely freely escape from that host environment. So again, like the normalization of this neutrino spectrum is set by the cosmic ray interaction rate, which is set by the cosmic ray energy density, and hence the star formation rate. And again, the spectral index is set by the underlying spectral index of the cosmic ray protons within the host galaxy. So we know what the emission is like from these kind of systems. Like, how do we model a background from this kind of information? Well, we can do a cosmological rate of transfer where we account for the absorption. So this is the pair production I mentioned of the extragalactic background light that reprocesses the radiation field. So you have an absorption term here, and then that's re-emitted at maybe slightly lower energies as the radiation, as the the produced pairs inverse scatter the EVL back up to gamma ray energies, but slightly lower than the gamma ray primary. And then of course we have the cosmological model here. For neutrinos, we can compare the approach, and it's a little easier because you don't have this absorption term. You just have the emission due to populations of luminous infrared galaxies, star-forming galaxies, or whatever, and you only have like losses due to adiabatic expansion. So then you can just solve these two equations and compute compute a diffuse background from a population of star-forming galaxies originating 0. So why am I talking about this? Well, I think actually legacy data surveys, catalogs that have resulted from this, particularly the NEP field, using Akari and stuff within infrared bands, can provide us with the kind of information we need to properly model the emission spectrum from neutrinos and gamma rays from these kind of galaxies and get an understanding as to whether this can account for the tension between the gamma and neutrino background. What we need for this is like a catalogue of luminous infrared galaxies or ultraluminous infrared galaxies where we have the far infrared luminosity, ideally some spectral information. And from this we want to get like the star formation rate and the gamma ray attenuation. And also we need information about the redshift. It doesn't need to be super accurate. Photometric is fine, like the uncertainties in other parts of the model is going to be much more severe. And then we can make a number of assumptions, so like the field that we're looking in is representative of the universe, some assumption about the completeness fraction of the population, and assuming that the infrared spectrum emitted from these galaxies can be modeled as a modified black body. And this allows us to compute the gamma ray emission as well as calculating the inferred star formation rate, the neutrino emission. And what can this tell us? Well, it could tell us whether we can resolve this background neutrino versus gamma ray tension. And even if it can't do that, it can allow us to constrain the fraction of high energy diffuse backgrounds that are contributed by luminous infrared galaxies compared to less dusty star formation galaxies, which would be quite interesting. And I think this is quite important. Firstly, because the data is already there, the models are already there, and by putting these two together, we can actually start to get some new insight into the high energy processes operating in these interesting environments. So that could tell us things about the role of cosmic ray feedback, and we'd be probing that very directly. We can also start to account for some of these unresolved tensions in the gamma ray versus neutrino background, and open this new window to probe cosmic ray processes in these kind of environments that hasn't been considered in detail before. So yeah, the data is basically already there. The models are more or less mature now. So I think there's a lot of potential to open this window and look at some of these high energy processes in dusty galaxies. Thank you very much for your attention.
Thank you very much. We have 3 questions on Slack. Can you go back to your slide 8? So Alvina asked, is the neutrino emission always lower than the gamma rays?
Yes.
If so, then is this predetermined by the allowed interaction channels?
So this is determined by so it's determined by the dominant interaction channel. So within a galaxy like this, the dominant interaction channel is the PP interaction. So this is very different from, say, like an AGN environment. And this means that you're injecting neutrinos at maybe slightly lower energies than you would in an AGN, which allows you to discriminate between the two environments, between the two sorts of populations. And actually, you can calculate the neutrino emission just by looking at the production rate of the different kinds of pions. So in this case, I used the inclusive cross sections of the pion production from Kelman 2006.
And Matt asked, he thinks that gamma ray background can be produced mainly by blazars and radio galaxies.
Right. It depends on the energy band. So, like at these kind of energies, there's debate. The consent. There's no particular consensus in the field at the moment. There's various ways in which you could try and separate out the blazar or AGN contribution from star-forming galaxy contribution by looking at things like anisotropies, to look at the redshift distributions and so on. There is scope for about 10, 20, 30, maybe even up to 50% of the flux to come from star-forming galaxies. I don't think this has been ruled out yet, so I think it's very important we should look at this. And of course, we do see gamma ray emission resolved from nearby star-forming galaxies, so I think there's a lot of motivation to look into